This time, we'll take our knowledge of utility functions and apply it to solve the consumer's optimization problem. One of the issues that's often raised with the approach that we're about to take is that there's no way anybody is actually doing all of these complex calculations in their head every time they go to the grocery store. And while that might be the case, like we said way back in the very first lecture, our objective isn't to get a perfectly accurate model, but rather just to get something that fits closely enough. And while this model may seem to make people out to be entirely self-interested, there's no reason why all the arguments in the utility function need to relate to personal consumption. So there's plenty of room within this model to account for altruistic behavior. We're going to show that when a consumer is maximizing utility, then they will consume goods in quantity such that the marginal rate of substitution equals the ratio of market prices, so that the rate that the consumer is willing to exchange the goods at equals the rate at which they can actually be exchanged on the market. We know that the utility function is the objective function we're trying to maximize. However, we need to include some type of constraint in order to make this problem interesting. Otherwise, the answer would always just be to consume as much as possible of everything. So we have exogenous variables I, which is income, and the prices Px, Py. The budget constraint that we're going to use says that the total amount spent on both goods, so Px times the quantity of x is how much I spend on x, Py times y is the total amount I spend on y, so this sum represents my total spending, has to be less than or equal to my total income. So I can't spend more money than I have. This is an inequality constraint. So a consumer could conceivably spend less than their total income. However, if I have a consumer who always prefers to have more stuff, then inevitably they're going to be able to find somewhere to spend any extra cash they might have. So we don't really lose anything if we treat the budget constraint as if it were an equality constraint. Written as an equality constraint, we can write it as y is equal to I over py minus px over py times x. So this is y as a function of x. That tells us that the slope of the budget constraint is going to be minus the ratio of the prices. We're going to show that the utility maximizing bundle is found at the point where the budget line lies tangent to the indifference curve, which means that the slope of the budget line minus px over py equals the slope of the indifference curve, which is minus the marginal rate of substitution, or that the marginal rate of substitution equals the price ratio. This diagram shows a budget constraint, and the intercepts are going to tell us how much of x or how much of y we could buy if we spent all of our money on that good only. The slope minus px over py is going to tell us how much y we need to give up in order to be able to afford one more unit of x with the same income. Technically, we don't need to stay on the budget line. We can choose any bundle within the shaded area. The bundles inside the shaded area are those where we're not spending our whole income. But there's no reason why we would do this, because if we always prefer to have more stuff, we're always better off spending our entire income, so the solution will more than likely be on the budget line. This diagram gives a rough sketch of how the consumer's utility maximization problem proceeds. The utility level U3 is not attainable. The entire indifference curve lies outside the budget set, so there's no way to get there. U1 is attainable, for example, if we chose point B, but it's not optimal because the indifference curve crosses the budget line there. That means the marginal rate of substitution is higher than the price ratio. And if we moved slightly down the budget line and we swapped some Y for some X, we're going to move to a higher indifference curve and be better off. If, on the other hand, we're at a point where the indifference curve is flatter than the budget line, then we would be better off with less X and more Y. Therefore, the utility maximizing bundle has to be at the point where the indifference curve lies tangent to the budget line. This represents the highest utility that the consumer can attain under the budget constraint that they face. Note that the tangency point is not guaranteed to be the solution unless we assume that we have diminishing marginal rate of substitution and therefore have convex indifference curves. Furthermore, we will not always have an interior solution and might end up with a corner solution. For example, if the marginal rate of substitution is everywhere greater than the price ratio, there's not going to be a tangency point, and our solution will be in the corner. This diagram illustrates how the tangency condition is not always sufficient for a maximum. At bundle C, the indifference curve is indeed tangent to the budget line, but this isn't the highest utility we can attain, as we can see that point B lies within the budget set but is above this indifference curve. The maximum utility is attained at another tangency point A. Here, the indifference curve is curved the right way so that the second order conditions are satisfied. This diagram illustrates a case where we would have a corner solution. Since the indifference curve is steeper everywhere than the budget line, the consumer is always better off trading Y for X. And the maximum utility is attained at the corner point E, where the entire budget is spent on X. Now, if we were to trace the indifference curve below the X-axis, then we could end up with a tangency point with a negative quantity of Y. So to find the corner solution, we need to include non-negativity constraints in our optimization problem. Mathematically, we can write the consumer's problem as maximizing utility as a function of the quantities of these n goods, subject to the budget constraint that my total spending is less than or equal to income. We can write out the Lagrangian as being the utility function plus lambda times I minus P1 x1 all the way up to Pn xn. If we take the partial derivatives of the Lagrangian, we're going to have n plus 1 first order conditions. So we're going to have 1 for each x. So we're going to have del u del x1 minus lambda P1 is equal to 0. The same will be true for all of the x's down to xn. And then we have the partial derivative with respect to the Lagrange multiplier, which is just going to give us back our budget constraint. To solve this problem, we look at these first order conditions. So we have lambda is equal to del u del x1 over p1, but it's also going to be equal to del u del x2 over p2, and so on for every good. From this equation, we have that the ratio of margining utilities between any good xi and any other good xj is going to be equal to the price ratio of these two goods, or the marginal rate of substitution of xi for xj is equal to pi over pj. As always, the Lagrange multiplier lambda isn't just a tool that we use to obtain this solution, it also has an economic interpretation. Here, lambda represents the marginal utility of additional income. Since the marginal utility divided by the price is the same for every good, if I received another dollar, I would get the same value no matter what I spent it on. Alternatively, we can interpret the first order conditions as stating that the price of each good is equal to the marginal utility divided by the shadow price lambda. That is, the marginal benefit that the consumer receives in dollar terms equals the price of the good. So the price equals the consumer's willingness to pay for an additional unit of good I. However, these conditions are only going to hold at an interior maximum. At a corner solution, then these non-negativity constraints, xi greater than or equal to 0, which we haven't even written out so far, these are going to be binding for at least one of the goods. By the complementary slackness condition, if one of the non-negativity constraints is binding, then one of the first order conditions, del L, del xi, is going to be slack. So this is going to be strictly negative. What this means is that the price is going to be higher than the marginal utility divided by lambda. So this means that the price is too high to justify spending money on this good, even if I'm currently consuming none of it. Let's look at an example of this with Cobb-Douglas. So here, the utility is x to the alpha, y to the beta. Now let's have these add up to 1. The Lagrangian, with our budget constraint pxx plus pyy is less than or equal to I, is going to be our utility function plus lambda times I minus pxx minus pyy. So our first order conditions are going to be this with respect to x, this with respect to y, and this with respect to lambda. To solve this, we let lambda equal this over px, or this over py. If we rearrange this expression, we have px over py is equal to this divided by this, and here we can cancel out. This just becomes 1 in the denominator, this cancels out, and this just becomes 1 in the numerator. So the price ratio, px over py, just equals alpha y over beta times x. If we cross multiply here, we can rewrite this condition as pyy is equal to beta over alpha pxx. And since beta is equal to 1 minus alpha,
18.
And we can plug this into the budget constraint to give us I is equal to pxx plus pyy, or 1 over alpha pxx. That is, pxx is equal to alpha times I, so the coefficient alpha from our utility function is going to represent the proportion of our overall budget that we spend on good x. That means that the remaining 1 minus alpha is going to be spent on good y. This is going to give us the demand functions x star is equal to alpha I over px, and y star is equal to beta I over py. Notably, both of these demand functions only depend on the good's own price. They're not affected by the other good's price. Now, this does make for a nice and clean mathematical result, but it doesn't really line up with how we expect people to actually allocate their budgets. With Cobb-Douglas, the share of income that I devote to each good remains fixed no matter what the prices are. This makes this model a little bit unrealistic. Let's now look at a slightly more involved example. Let's look at CES utility with delta equals 1/2. Now, strictly speaking, this whole thing should be squared, but as always, we can apply a transformation to the utility function to get rid of that. We can set up the Lagrangian just like before. So we have L is equal to the utility plus lambda times I minus Pxx minus Pyy. And we can write out the first order conditions. So we have this with respect to x. We have this with respect to y. And the first order condition with respect to lambda will just give us the budget constraint again, so we won't write that this time. From these two equations, we're now going to have that lambda is equal to 1 over 2 square root of x times px is equal to 1 over 2 square root of y py. If we rearrange this condition, we get that px over py is equal to the square root of y over x, or we can write that as y is equal to px over py squared times x. If we plug this into the budget constraint, we get that I is equal to pxx plus py times px over py squared times x, or pxx times 1 plus px over py. And that's going to give us the demand function x is equal to I over px times 1 plus px over py. If I then plug this into here, I get that the demand for y is equal to I over py times 1 plus py over px. So what do these demand functions mean? We can see that the share of income I spend on x, so px times x, is not going to be constant, but is going to depend on the relative prices of x and y. As x becomes more expensive relative to y, the demand for x is going to decrease, not just because the consumer is spending the same amount of money on less quantity, as it would be the case in Cobb-Douglas, but also because they're shifting some of their spending away from x and towards y. Looking at a couple of more examples, let's say we have CES with delta equals -1. So that means the utility is equal to -1 over x minus 1 over y. This time, we'll skip the whole process of setting up Lagrangian and taking the derivatives, and just use the result that the price ratio is going to equal the ratio of marginal utility. So here that's going to be px over py is equal to 1 over x squared over 1 over y squared, or y over x is equal to the square root of px over py. So from here we get that pyy is equal to square root of py over px times pxx. And if we plug that into the budget constraint, we get that I is equal to pxx plus square root of py over px times pxx. And this will give us the demand functions. X is equal to I over px times 1 plus the square root of py over px. And y is equal to I over py times 1 plus the square root of px over py. Again, the share of income that I spend on each good is going to depend on the relative prices py over px. If we have delta equals minus infinity, we're going to have a fixed proportions utility function. So let's have one where the utility is the minimum of x and 4y. Now, if we were to try the usual approach of taking the ratio of marginal utilities, that's just going to give us 0 over 0. So we have to use a bit of intuition here. Now, with fixed proportions, if I just consume more of one good while holding the other fixed, that gives me no additional benefit. That means that I always want to make these two arguments equal. So I need to keep x equals 4y. And then we can plug this into the budget constraint. So I have I is equal to pxx plus py times x over 4, or 4px plus py over 4 times x. This is going to give me the demand functions. X is 4i over 4px plus py, and y is just going to be x over 4, so I over 4px plus py. An easy way to think about this case is that the consumer is always going to buy blocks that consist of 4 units of x and 1 unit of y per block. The price of one of these blocks is going to be 4px plus py, and the demand for y is going to equal the number of blocks that I buy, while the demand for x is going to equal 4 times the number of blocks that I buy. So far, we've written utility as a function of the quantities of goods that I consume. But if I solve the consumer's problem, I can get their demand functions in terms of the exogenous variables, which are the prices of each good along with the income level, and I can get solutions for each x. If I then plug these demand functions into the utility, I can get the utility in terms of these exogenous variables as well. This is called the indirect utility or the value function. So I have u of x1 star of p1 through pn and I, all the way through to xn star. And I'm going to call that v, which takes its arguments all of the prices and income. This v is going to be my indirect utility function. What the indirect utility function says is that no matter what the prices and my income are, I'm always going to choose the optimal bundle given by these solutions x1 star through xn star, and therefore I'm going to achieve the maximum utility that's possible given these exogenous values. One application of the indirect utility is that we can analyze the welfare effects of taxes. If we assume that consumers are always going to optimally rebalance their budgets whenever prices change, then the indirect utility is going to tell us how well off they'll be after the imposition of a new tax. The lump sum principle is going to say that an income tax is always better than a tax on a specific good that raises the same amount of revenue. Why? Because when I tax a good that's going to have the additional effect of distorting the relative prices, which means that consumers are going to shift their spending away from the tax good in order to avoid paying the tax. This means that the tax is going to raise less revenue than expected, or that we are going to need a higher tax rate than we think in order to raise the same amount of revenue. If we take a look at this diagram, without taxes, the consumer is going to be at the bundle X star, Y star. So if we impose a tax only on X, that's going to tilt the budget constraint. It's going to keep the y-intercept the same because the price of y hasn't changed, but it's going to increase the slope and decrease the x-intercept because now the price of x is higher. At this new budget line, the consumer is going to choose the bundle X1, Y1. They're going to shift most of their spending towards Y in order to avoid having to pay the tax. Now, consumers would be better off if this tax were just replaced with an income tax, because this would shift the budget constraint in, but would keep the slope the same. The relative prices wouldn't change. We're going to set the income tax just high enough so that the consumer can still afford X1, Y1, ensuring that it's going to collect the same amount of revenue as the sales tax. But if we impose an income tax that collects the same amount of revenue, the consumers now have a different choice and they'd rather pick X2, Y2 instead. That means that with an income tax, while they could afford to consume the same bundle they would have chosen under the sales tax, they can pick a different bundle that gets them to a higher utility level, which is going to make them better off. We can find some indirect utility functions from the examples that we looked at before just by plugging the demand functions into the utility. So for Cobb-Douglas, if we have alpha is equal to beta is equal to a half, then I have x is equal to I over 2px, and y is equal to I over 2py. If I plug this into the utility function, I'm going to get that v of px, py, I is going to equal I over 2 times the square root of px times py. For the fixed proportions, we had x was equal to 4i over 4px plus py, y was equal to I over 4px plus py. If I plug that into the utility function, which was the minimum of x and 4y, I'm going to get that the indirect utility is just equal to x or 4i over 4px plus py. So let's suppose that I is equal to 8, px is equal to 1, and py is equal to 4. In the Cobb-Douglas case, and let's say alpha is equal to beta is equal to 1/2, the consumer is going to spend an equal share of income on both goods. So they're going to spend 4 on x and 4 on y, which means that x is going to be 4 and y is going to be equal to 1. Plugging that into the utility, that's going to give us an indirect utility of 2 at these parameters. Now let's assume we impose a tax of 1 on x. So the after-tax price goes to 2. That means we're now going to buy 2 units of x, while y is going to remain at 1. The new utility is now just going to be square root 2, or about 1.41. Because the consumer is going to buy 2 units of x, the total tax revenue, Tx, is going to be equal to 2. Now let's assume that instead of having a sales tax, we collect the same revenue as an income tax. So income, it goes down to 6, while the prices remain the same. Given these parameters, the consumer is once again going to spend the same amount on both goods. They're going to spend 3 on X, so X is equal to 3, and they're going to spend 3 on Y, so Y is equal to 3/4. This is going to give an indirect utility of 3/2, about 1.5. So we can see that the utility under the income tax is higher than the utility under the sales tax. If we were to look at the exact same example with a fixed proportions utility, we would not get the same conclusion. Each block consisting of 4x and 1y is going to cost 8. So I'm going to buy one block. That means x is equal to 4, y is equal to 1. If I impose a sales tax, so the price of x goes up to 2, then the price of a block is going to go up to 12. That means the consumer can only afford 2/3 of a block, so x will be 8/3, y will be 2/3. The utility here is going to be the minimum of x and 4y, so the utility will be 8/3, and the total tax collected will be 8/3. If instead we were to impose an income tax, so the income goes down to 16/3 while keeping the prices the same, once again, we're only able to buy 2/3 of a block. So I have 2/3 of y and 8/3 of x, which means that the utility is equal to 8/3. That means that if I have a fixed proportions utility, then the consumer will be equally well off whether I impose a sales tax on X or whether I impose an income tax that collects the same revenue. The reason for this is that when the goods are perfect complements like this, they always have to be consumed in fixed proportions. So the consumer can't shift their spending between goods when the prices change. That means that there's not going to be this kind of substitution we saw in the previous example, and so the welfare effects of an income tax and a sales tax will be the exact same. In the utility maximization problem, we restrict the level of spending and try to reach the highest level of utility. But like any other optimization problem, it has a dual problem where we switch the objective function and the constraint. This is the expenditure minimization problem. Here, we instead are going to impose a target utility and find the minimum level of spending necessary to reach it. So we're going to minimize our total expenditure, which equals the spending on each good, subject to the constraint that I reach a utility of at least U bar. The solution to this problem gives me the expenditure function, which tells me the minimum expenditure given the prices and the utility level I'm trying to reach. This diagram demonstrates the expenditure minimization problem. Rather than fixing the budget line and trying to get to the highest indifference curve, we're instead going to fix a utility level at the target and then try to find the lowest expenditure line. E1 is too low. That's not enough money to reach our utility target, while E3 is too high since it crosses the indifference curve. So E2 is just right. It lies tangent to the indifference curve. This is going to give us the same solution as the utility maximization problem. If we fix the budget at E2, the maximum utility we can get to is U2. The expenditure and indirect utility functions are inversely related, since higher prices will require more spending to achieve the same utility, while reducing the maximum utility achievable under the same income. Expenditure functions have a few useful properties. They're always going to be homogeneous of degree 1 in prices, since if we were to double the price of every good while keeping the target utility unchanged, the total spending required would also double. They're also going to be non-decreasing in prices. If we increase the price of a good, that will cause consumers to substitute toward other goods, but this reshuffling can't save us so much money that we actually end up spending less than before when the prices are higher. And the expenditure function is concave in prices. The expenditure function would be linear if consumers never adjusted their spending in response to price changes, but because they do adjust, the expenditure function is going to lie below the straight line. By the principle of duality, if U is the highest utility I can achieve given income I, then I is going to be the minimum expenditure necessary to reach the utility level U. So in Cobb-Douglas, we had an indirect utility function V was equal to I over 2 square root of px times py. If we set this equal to u bar, then we rearrange, we get I is equal to 2 square root of px times py over u bar. This will give us the expenditure function for the dual expenditure minimization problem. So this is equal to E of px, py, u bar under Cobb-Douglas. We can also do this with a fixed proportions utility. So the indirect utility function there was 4i over 4px plus py. Let that equal to u bar. That's going to give me I equals px plus py over 4 times u bar. This is going to be my expenditure function. Now, I'll leave it up to you to verify that these answers are the same ones that you would get if you set up the Lagrangian for the expenditure minimization problem, solved it, and then plugged the demands back in to get the expenditure function directly. This diagram demonstrates why the expenditure function must be concave in prices. Let's fix the price of every good except for x1 and changed only p1. Then the expenditure would be p1 times x1 plus other stuff. That means that if the consumer never adjusted their spending in response to price changes, their expenditure would be linear in p1, which follows the line E pseudo. However, assuming that they actually do make these adjustments, their actual expenditure should be lower than this. So their expenditure function is going to lie below the tangent line. In the next chapter, we'll look a little bit more closely at how exactly individuals are going to respond to changing prices.